Okay, team, I know that and it can be very interesting during these times. So this is just a really quick recap of the basics. That way, when you go to the slides and look through it, you can easily do it. Okay, so first we started off revising what we've done. Okay, so really do a look, cover up, check what did you prefer, and then you might want to compare it to what the properties of acids and bases are. So please pause this and have a go. Next up, we just look at the Bronson-Lowry or the Lowry-Bronson acid-base theory, and essentially we actually had two guys who actually came up with the same theory independently at about the same time, which is something that tends to happen in science. Okay, so they both actually said acids are a molecule. They are a molecular ion that actually donate your protons, okay, or your hydrogen ions, while bases are the ones who accept these protons or hydrogen ions. All right, so if you have to define a Bronson-Lowry base, it is a proton acceptor, and a Bronson-Lowry acid is a proton donator. Okay, so if you look at this example here, we just have a base reacting with water, and as you just learnt, your base is accepting the proton and your acid has donated it. Okay, as a result, we have something called our hydroxide ion forming. Okay, just a really important theory, a bit of terminology here. You may see the word your alkaline bases. Okay, with your alkaline bases, they are actually within the category of bases, but unlike your normal bases, they're a group that are actually soluble in water, because most bases are actually not soluble. They're also quite slippery as well. So we also mentioned something called our hydroxide ions, but if you have a acid, you actually have something called a hydroxide ion. So when you actually have the hydrogen joining, you have the formation of this guy here. And we actually use our hydrogen ion as a short form of this to make it simpler and easier. So you will have to get a little familiar with seeing this. This is just a nice way of remembering what we call a conjugate base or a conjugate acid. So for example, acid here is, remember, the generous one donating the hydrogen is then later called our conjugate base, and our base here, who's the one who grabs that hydrogen, is called the conjugate acid. Okay, just some examples of some acids and what they do when they donate a proton, what they become. Remember, as a conjugate base, and then as these bases who accept protons to become that conjugate acid. And we've also got something where you've got a substance that can behave as both an acid and a base depending on who it is reacting with. And one example of this is water. As you can see, water is actually accepting and becoming a hydronium ion, and then you've got water actually donating and becoming a hydroxide ion, and this is what we use to describe an amphiprotic substance. That is what an amphiprotic substance does. It can behave as both. So let's look at some more examples here. And we also have something that we call monoprotic acids and polyprotic acids. Basically, these are acids who can either donate only one hydrogen, as you can tell in hydrochloric acid there's one hydrogen here, or polyprotic, where it can donate more. Poly is more than one proton. And in this example of sulfuric acid, how many hydrogens can it donate? There's two. That is why we use the word diprotic. Okay, and if it's got three, we would use the word triprotic. It just describes how many hydrogens this acid can donate. Please keep in mind, however, that the first time it donates the hydrogen, it does so quite easily. The second time, it actually needs more energy. Okay, so it becomes more and more difficult each time this polyprotic acid has to donate each hydrogen ion. Okay, so it requires more energy. Just a quick recap, team, of what you need to focus on with this lesson. Make sure you jot down the definitions over here, okay? And also, I want you to learn the formula for these acids and bases, and also just use examples of different amphiprotic substances and polyprotic substances. What is the difference, between the two, amphiprotic and a polyprotic substance? So these are just some examples of common acids and bases that will help you answer those questions. Next up, we then looked at the strength versus concentration dilemma. Okay, so the strength of something is how is it able to accept or donate protons? What's that relative tendency? okay? If you look at concentration, it's actually more of a quantitative, what is the amount of the solute dissolved in the solvent? Okay, so they're really looking at different things, although sometimes they can get a bit confusing. So if we look at the strength of an acid, it's really how easily does the acid or base either donate or accept the proton. Okay, we use another word of saying how completely does it ionize into its conjugate ions. So please make sure you do get used to this terminology. So when you have something like your acid forming your your hydronium, you can say that it's actually a stronger acid. Okay, I think I confused that a bit there, but just keep in mind that there are different strengths of the acids and bases. So let's look at some different types here. So if you've got a strong acid, we say it's completely ionized in water. If it's a weaker acid, it's partially ionized. And we actually use these double-headed arrows, which kind of shows you that it's not definitely pushing in one direction. It can go the other way as well. So one example of a strong acid is your hydrochloric acid. Your weak acid is something like ethanoic acid. So just for a bit of context, if you're looking at a weak versus a strong acid, you've literally got something that you say it's virtually 100% ionizes versus it doesn't completely ionize, okay? So you get many hydronium ions being formed if it's a strong acid versus just a few hydronium ions, okay? A lower pH, because remember your pH, the lower it gets, the more acidic it is, the higher the concentration of hydronium ions are found. And then you've also got the conduction of electricity affected, because remember, electricity actually relies on how many free moving charge carriers are in the solution, okay? So take a minute to jot those down and understand that. Same goes for bases, okay? If they're strong, they accept the protons easily, forming more of the hydroxide ions, not the hydroniums this time, and they have higher pHs, vice versa for your actual weak bases. So let's maybe look at some examples, all right? Got some strong, weak acids, important ones to keep in mind, and just have a look at what happens. So the stronger your acid is, the weaker the actual conjugate base would become, okay? So keep in mind how that works there. Now, if you look at concentration, just to clarify, it's the amount of solute in your solvent, okay? So if you dilute it, the concentration actually, what do you think is going to happen? It actually decreases because it's actually describes what it is, all right? Then you can look at the quantitative version of it, which we've learned earlier with the N equals CV formula, which can be transposed into the C equals N divided by V formula, and it gives us a numerical value for this, okay? So if you kind of say it's dilute, you can also mention the concentration of it as well, okay? And lastly, we were also looking at the acidity of solutions, and this is measured by something that we call the pH scale. So the pH scale is actually developed to look at the acidity of a certain solution. It measures the concentration of the hydronium ions, okay? Just note, however, the equation used. You've got a negative at the front and it's to the log. So the reason we use a logarithmic scale is because the numbers are actually really quite different, okay? But they're changed by a factor of 10 each time you go from pH of 1 to maybe pH of 2. As a result, it's a lot more easier to use numbers like a pH of 1 versus a pH of 2 instead of using numbers that are changing by tens, all right, which is why we use the log. Also, it's kind of funny when you think about pH being the concentration of hydronium ions, but when you've got a very acidic solution, it's got like a pH of 2, right? Doesn't quite make sense. The reason for that is because we've got the negative sign here. It's an inverse, all right? So that's why it might actually trick you a bit, but just keep in mind that it's an inverse. As a result, if it's got a high concentration of those hydronium ions and it's quite acidic, it's going to have a low pH value, okay? Just an example here. Take a look at a quick summary, which you may remember from the past. Neutral means a pH of 7, acidic means it's lower than 7, basic means it's higher than 7, okay? And look at some examples here. Rainwater itself, quite acidic. I want you to note, however, here, look at the concentration of the hydronium ions, okay? Then look at the hydroxide ions. If you combine them together, what do you get? So using this information, we don't have to worry about this as much, but you can actually, using the hydronium ions, work out the concentration of the hydroxide ions, okay? This is just a nice example, a nice visual representation of the pH scale. You may see some familiar things like your tomato juice, your vinegar, your coffees, quite acidic, getting more and more acidic as we go. Then you've got things that are more basic, like your ocean water, your hand soaps, and your bleach. How do we measure this? So we actually use something which we call our indicators, okay? So these are usually chemicals, and depending on what chemical you use, they change a range of colors to tell you what the pH of that solution is. Now, usually their range is quite limited, which is why we can also use our universal indicator, which is a mixture of these chemicals, and they kind of give you a greater range, okay, to be able to look at the pH values. However, they don't really give you that numerical number. So if you want that more accurate numerical number, you would use something like a pH meter. Just to start wrapping up, I want you to think about what's the impact of diluting a solution on its pH value. Okay, so let's say that I've taken a solution of water and let's say an acid, and I add some more water in. What do you think is going to happen to the concentration? So to help us understand that, we have to take a step back into remembering the mole and the concentration, how we can work out the concentration using the mole. So it's a mole divided by the volume. So the bigger the volume gets, what do you think is going to happen to that concentration? That's where we can actually go back to this formula here. The first concentration, the first volume, and then the second volume and that concentration. So essentially what happens is the greater the volume becomes as you dilute it, the concentration is also going to drop. Okay, you're going to have less of that hydronium ions in the solution, and just keep in mind that as your hydronium ion concentration drops, the pH is going to actually increase. Why is that? Let's have a look back to the actual formula used, which is here, negative or log. So just keep in mind that although in your head, I know you're realizing the concentration's dropping, but as the concentration drops, when you dilute it, the pH increases, okay? Just another visual representation of that. As the concentration drops, the pH increases. So an example is you add 10 mils of water to 1 mil of acid, and it may go from 1 to 2. Okay, and just remember for bases, it's just the other way around.